Nice. Okay, well, this is really excellent. It turns out that if you do this thing and you have the list of the coolest questions in mind ahead of time, if you do this activity, it turns out you get pretty much all the coolest questions every time, especially with a group as sharp as this one. But there's a different feeling about it when it's your question instead of my question, right? I really like this feeling of kind of creating a problem situation, maybe with a little vagueness about it. I think somebody was complaining, yeah, see, this is not really a question about the problem. It's a question about the situation. Like, are the cards that come out still cards that are reusable? I think I'm going to say definitely yes. So we'll answer that one really fast. Okay, so one's done. But the rest of these, I mean, look at these great questions. What's the smallest number you can't make, or in general, right? This is kind of these two kind of go together in terms of what numbers are unmakeable. You can imagine, what if you had the infinite set of cards with all the counting numbers, right? What numbers are possible outputs of the machine and what numbers are not possible outputs of the machine? Could be a pretty interesting question. Then these two certainly relate to each other, and this one, right? So these are all about, oh wait, no, this one relates to this one. Right? Those three are connected, right? And what is the set of all outputs? Okay, so we got the same question essentially a bunch of times, which is an interesting thing. These two you've already marked for me are pretty much the same question. If the outputs are unique, then you can find x and y from the outputs, but if there's different sets of inputs to make the same output, then the process isn't reversible. I think this is a really important thing. Like, I think maybe as geometry teachers, some of us learned whenever you give a definition of something, you should always give examples and non-examples so the kids can start to see, oh, that's what it is, but you don't really understand what it is until you know what it isn't. And in the same way, if you have any kind of procedure you can do, to me, like, what was the big difference between when I taught sort of the regular classes and the honors classes is that in the regular classes, I would have to show them, like, take A and B and get C, take A and C and get B, take B and C and get A as like three different problems that they could think about. And in honors classes, I would show them with A and B, you get C, and then I would expect them to figure out for themselves that you could turn it around and reshuffle it all other ways. And so then that started being something that I would consciously try to teach all the kids to do, because that to me was like the big difference in ability, was just that way of naturally thinking of these kind of questions you came up with, like, can you invert this process? How can you work backwards in different ways? Maybe the output by itself is not enough, but maybe if you know the output and you know x, you can find a nice formula to find y at least, right? It's like 2 out of the 3 things. There's x and there's y and there's the output. So if you know any 2 of them, can you find the third one? And so all these kinds of questions are really good. So this one, so what you're saying is, like, after I took the 6 and 8 and I made 62, that would like let me throw away the 62, whoever's question this is, that would like let me throw away the 62 card. I've cleaned the 62 card out of my package. Does that make sense? So I got rid of the 6 and the 8, and then because I got 62 as the answer, I'd throw away the 62. Can we get rid of all the cards? Can somebody answer this question in the next 8 seconds? Go. No, because 100 is not divisible by 3. Exactly. Okay? So.
But what if you get an output that isn't there anymore? Then.
Oh, so we don't have to get rid of xy plus x plus y. Like we get something else that makes another 62, and then 62 is already dead, so we don't need to worry about it. Something like that. Yeah. So it could become a more interesting kind of question. But that divisibility by 3 idea, that at least for me is what I was thinking of as the meaning of this question, but I agree we could have it mean other things too. Also goes into this, like, when is the output even or odd, right? That's first step at trying to think about these things, is how can we tell, right?
I think our middle school kids, on that last question, I teach middle school, like, don't understand the operation of the integer, just like looking at that operation we put in there, like the x times the y, that's got to be an odd times the even number if they're consecutive. To understand, I have a lot of middle school kids, I think. You always know we multiply 2 numbers, or two negatives make a positive, but they don't know if it's multiplication, addition. I have two kids that add two negatives. Well, two negatives make a positive, but they don't quite get the operating application algebra. So if they don't have that understanding, it makes algebra a lot more difficult.
Yes.
But just to understand that has to become every time used to, because they never an odd answer, and they have to explain that. I'm making guess and check and figure out that it's odd every time. Okay, but why is it odd every time?
Right. Yeah, I mean, around here, it kind of goes without saying that we need to have the why part. With the kids, you need to remind them a lot that you need to have the why part, yeah. So this odd and even thing is an interesting question. And so now that the answer to this is yes, now this question makes sense, right? If we keep doing this process, what happens? Well, eventually we get down to just one card, right? So that we can try to sound more exciting by calling that a monovariant, something that always varies in the same direction. Namely, every time we use the machine, we have one less card than we had before, so the number of cards is always decreasing every time we use the machine. And so as long as there's at least two cards, we can feed them to the machine. And then when we put in two cards, there's only one left. So no matter what pile of cards you start with, if you keep doing stuff, eventually you have one card. So I think that's the question that conveniently happens to be at the top of the list here. But I think this is a question I want to focus on. But a lot of these other ones you might make discoveries about on your way while you're exploring this one. Or you might notice something that kind of sidetracks you onto one of these other ones, which is pretty good. So I want to focus on this first question, which is, what happens if we use this machine and we keep feeding it cards and eventually we get one card out? What are the possible final results? And what's the largest is an interesting question, or what's the smallest, or is it even, is it odd? Are there some numbers you know it can't be? Because there's some numbers that are never outputs. So you see how all these other questions can kind of tie into this one a little bit, right? Maybe the first thing you figure out is whether this final number has to be even or has to be odd or something like that. And I think the other key thing to mention probably now is, the people here come from different math backgrounds. We have middle school teachers, we have professional mathematicians. Some professional mathematicians are really good at specializing in their field and are not always the best when you take it to this particular kind of problem solving, and other mathematicians are real problem solving experts, and you give them any kind of problem that builds on basic knowledge like this, and boom, they're going to get it. So the question is, how are you going to structure your group so that everybody has fun, nobody feels left behind, everybody has some opportunities to discover stuff? And in general, from my point of view, you're going to see me practicing this as I wander around to your groups, but there's the famous Dan Meyer quote. Those of you who know Dan Meyer, I don't know, that he's a well-known math blog guy. He says, be less helpful. Because the urge is always, oh, I know all this cool stuff about this problem and I want to tell you all about it because it's awesome. And as soon as I start telling you all about it, you're no longer learning anything because I'm just here talking about stuff. You're not solving any problems. You're not figuring any stuff out. And so the key trick, you don't want to be unhelpful, of course, but the urge is always to be too helpful, and reminding yourself to be less helpful is always important ones. All right, so we're going to try to answer this first question in the next hour or so, if we can manage that. So that's kind of our approximate time constraint. So go for it.